The story begins with a quiet, patient machine far from Earth, its giant mirror unfolding like a silver flower in the darkness of space. The James Webb Space Telescope slowly turned its powerful instruments toward a small and fast-moving visitor named 3I/ATLAS. On that moment, Webb was not just looking at another comet. It was studying an object that did not come from our solar system at all. This visitor had traveled for millions, maybe billions of years through deep space before briefly passing through our cosmic neighborhood. Webb's infrared vision allowed scientists to capture new images and data that revealed details never seen before, giving humanity a rare look at material formed around another star. To most people, a comet looks like a fuzzy dot with a glowing tail. But to scientists, a comet is a frozen record of history. Inside its ice and dust are clues about the environment where it formed. Comets from our own solar system tell the story of how the sun and planets were born. But an interstellar object like 3I/ATLAS is even more special. It carries material from a completely different star system. Webb was designed for moments like this. Its ability to see infrared light means it can detect heat, gases, and chemicals that normal telescopes cannot see. When Webb focused on 3I/ATLAS, it detected glowing signatures of gases surrounding the object, especially carbon-based compounds. What Webb collected were not just beautiful images, but detailed light patterns called spectra. These patterns act like fingerprints for different molecules. By studying them, scientists could tell which gases were present around the comet. The data suggested that 3I/ATLAS contained a large amount of carbon dioxide and other carbon-rich materials. This was important because it hinted that the comet formed in an extremely cold region of space. Such environments allow these volatile materials to freeze and remain trapped for billions of years. The chemistry seen around 3I/ATLAS looked different from many comets we know, suggesting its home system may have evolved in a unique way. Webb's observations did not stand alone. At the same time, other telescopes on Earth and in space were watching the comet. Some captured it in visible light, showing a soft cloud of dust around a small, bright core. Others recorded its motion across the sky, creating time-lapse views that made the comet look alive as it raced through space. When scientists combined all these observations, they gained a fuller picture of the object. Each telescope revealed something different, like puzzle pieces slowly fitting together. One of the most surprising things scientists noticed was the comet's behavior. Instead of releasing gas and dust evenly, 3I/ATLAS showed powerful jets shooting material outward. In some images, these jets appeared oddly shaped or pointed in unexpected directions. This suggested the comet was spinning, and that certain areas on its surface were more active than others. Some changes happened quickly, within hours or days, indicating that the nucleus was rotating faster than many typical comets. These movements helped scientists estimate how the comet was structured beneath its surface. Webb's infrared data also allowed scientists to study the dust in detail. Dust grains glow slightly when warmed by the sun, and Webb can detect that faint heat. By analyzing this glow, researchers learned about the size and composition of the dust particles. Some appeared small and fresh, while others looked older and more compact. This information helps explain how violently material is being released and how long the surface has been exposed to space. For an interstellar object, this matters because it has spent most of its life far away from any star. As 3I/ATLAS moved closer to the sun, its activity increased. Frozen gases turned directly into vapor, pushing dust outward and forming a bright coma. Observations showed sudden bursts where the comet briefly became brighter, followed by changes in its jet patterns. These events suggested pockets of volatile material beneath the surface that were suddenly exposed. Watching these changes helped scientists understand how heat travels through the comet and how its structure reacts after such a long journey through cold space. Behind the scenes, scientists around the world worked quickly. Interstellar objects do not stay long, and every observation counts. Teams coordinated schedules, shared data, and checked each other's results. Modern astronomy relies on this global teamwork. The ability to respond quickly and combine observations from many sources is what made this study so successful. It showed how prepared the scientific community has become to study rare and fast-moving objects. One big question remained: where did 3I/ATLAS come from? The chemical clues suggested it formed in a cold outer region of another planetary system. That region may have been rich in carbon and other ingredients important for complex chemistry. This raised exciting possibilities. If such materials are common around other stars, then the basic building blocks for life might also be widespread throughout the galaxy. While this does not mean life exists elsewhere, it strengthens the idea that the chemistry needed for life is not unique to our solar system. Another mystery was how the object escaped its home system. Most likely, it was thrown out by gravitational forces, possibly from giant planets or passing stars. Once ejected, it drifted through interstellar space for an incredibly long time. During that journey, it was exposed to cosmic radiation and extreme cold. Yet, despite this harsh travel, much of its original material survived. This balance between change and preservation fascinated scientists, offering clues about how interstellar objects age over time. Other types of observations added even more depth. Some instruments detected faint energy emissions caused by interactions between the comet's gases and the solar wind. This showed how the comet responds to the charged particles streaming from the sun. By studying these interactions, scientists learned more about how much material the comet was losing and how energetic its environment had become. Each wavelength of light told a different part of the story. The images released to the public captured imagination worldwide. They showed glowing clouds, fine dust structures, and a sense of motion frozen in time. Although these images were processed so humans could see them, they represented real physical features. People everywhere were reminded that this was not just a distant object but a traveler from another star system briefly visiting ours. Estimating the size of the comet's nucleus was challenging. The bright dust cloud made it difficult to see the solid core directly. However, by analyzing brightness and motion, scientists estimated that the nucleus was likely several kilometers wide. Knowing its size helped explain the strength of its jets and how much material it could release without breaking apart. These measurements also helped compare it to comets from our own solar system. As the data continued to be analyzed, scientists noticed both familiar and unusual traits. Some aspects of 3I/ATLAS behaved like comets they had studied before. Others did not. Its chemical balance and dust behavior stood out. This reminded researchers that one object cannot represent all interstellar visitors. Each one is shaped by its unique history. Still, Webb's observations provided a strong reference point for future discoveries. The success of these observations highlighted the importance of preparation. Modern survey systems are improving at spotting unusual objects early. This gives scientists more time to study them. Webb's role showed how powerful space telescopes can respond when rare opportunities appear. Some researchers are already thinking ahead, imagining spacecraft that could chase and study such objects up close one day. While difficult, the idea no longer feels impossible. For the public, the meaning was simple and powerful. Humanity had observed material from another star system in remarkable detail. It was a reminder that our solar system is part of a much larger, connected galaxy. These moments help people feel connected to the universe and curious about what lies beyond. Even though 3I/ATLAS is now moving away, its story is far from over. Scientists will study the data for years. They will compare it to future interstellar visitors and refine their models. Every analysis adds another layer of understanding about how planetary systems form and evolve. In the end, the images captured by the James Webb Space Telescope were more than scientific data. They were a glimpse into another place, another time, and another star's history. They showed what is possible when advanced technology meets human curiosity. As Webb continues its mission and new visitors are discovered, this moment will be remembered as an important step in exploring worlds beyond our own. The universe sent us a visitor, and for a brief moment, we were ready to look closely. As the comet continued its journey away from the sun, scientists knew that every hour mattered. Interstellar objects do not slow down. They pass through, reveal themselves briefly, and then disappear back into the deep dark between stars. This made the data collected by the James Webb Space Telescope even more valuable. Each pixel, each faint glow captured in infrared light, was a message sent across unimaginable distances. Scientists treated the information carefully, rechecking calculations and comparing results, knowing that this opportunity might not come again for many years. One of the most fascinating aspects of 3I/ATLAS was how calm and violent it seemed at the same time. From a distance, it looked peaceful, gliding silently through space. But up close, it was active, shedding gas and dust, releasing energy, and reacting strongly to sunlight it may not have encountered before. This contrast reminded scientists that space objects are not static rocks. They are dynamic, changing bodies shaped by their environment. For 3I/ATLAS, that environment suddenly shifted when it entered our solar system. Before arriving here, the comet likely spent millions or even billions of years in near total darkness. The space between stars is cold beyond imagination. Temperatures there are only a few degrees above absolute zero. In that environment, chemical reactions slow down and ice remains frozen solid. When 3I/ATLAS approached the sun, that long frozen material began to wake up. Gases trapped inside the ice started to escape, pushing dust outward and forming the glowing cloud Webb was able to observe. It was as if the comet was breathing for the first time in ages. Scientists were especially interested in how quickly this activity began. The early signs suggested that 3I/ATLAS responded strongly even when it was still far from the sun. This hinted that some of its ices were extremely sensitive to heat. That sensitivity supports the idea that the comet formed in a very cold region of space. In warmer regions, such volatile materials would not survive long. This detail helped researchers narrow down the possible birthplace of the object. Another detail that stood out was how uneven the activity appeared. The jets did not come from all directions. Instead, they seemed focused in specific areas. This suggested that the comet's surface was not uniform. Some parts were likely covered in a thick, hardened crust, while others had cracks or thin layers that allowed gas to escape more easily. Over time, these weak spots become more active, shaping the comet's behavior. This uneven surface also explained the changes in brightness that telescopes recorded. As scientists modeled the comet's rotation, they noticed that the jets appeared to swing back and forth. This movement suggested the nucleus was spinning, possibly wobbling slightly as material escaped unevenly. This process can slowly change how a comet rotates, sometimes speeding it up or slowing it down. Over long periods, such forces can even cause a comet to break apart. Watching these effects in real time gave scientists insight into how small bodies evolve under stress. The dust released by 3I/ATLAS told another story. Some particles were tiny, almost smoke-like, while others were larger and heavier. The mix of dust sizes helped scientists understand how the material was released. Gentle gas flow produces fine dust, while stronger outbursts can lift heavier chunks. Webb's infrared sensitivity made it possible to detect warm dust even when it was faint. This helped researchers measure how much material the comet was losing overall. There was also curiosity about whether the comet showed signs of organic molecules beyond simple gases. Organic compounds are molecules that contain carbon and are considered important building blocks for life. Webb's instruments are capable of detecting such compounds, and early analysis hinted that complex chemistry might be present. While this does not mean the comet carried life, it does suggest that the ingredients for life can form in many different environments. This idea excites scientists because it supports the theory that life-friendly chemistry could be common across the galaxy. As news of Webb's observations spread, the public response was immediate. People shared images, asked questions, and expressed awe at the idea of studying material from another star system. For many, this was the first time the concept of interstellar visitors felt real, rather than theoretical. It was no longer just science fiction. It was something humanity could observe, analyze, and understand, at least in part. Teachers used the images to explain how telescopes work. Students learned how infrared light reveals things invisible to the human eye. Artists found inspiration in the glowing shapes and colors. Writers imagined stories about where the comet came from and what it had seen on its long journey. In this way, 3I/ATLAS became more than a scientific object. It became a symbol of exploration and curiosity. Within the scientific community, discussions grew deeper. Researchers debated how typical or unusual this object might be. Was 3I/ATLAS a rare oddity, or was it representative of a large population of similar objects drifting between stars? The answer matters because it affects how scientists estimate the number of interstellar objects passing through our solar system at any given time. If objects like this are common, then our solar system may be visited more often than previously thought. Some models suggest that billions of small bodies could be roaming the galaxy, ejected during the chaotic early stages of planetary formation. Most would never be seen. Only those passing close enough to the Sun and Earth would become detectable. This means that what we observe is only a tiny sample. Each interstellar object studied helps refine these models, improving our understanding of how planetary systems evolve and interact. There was also discussion about how future telescopes might improve on Webb's work. While Webb is extremely powerful, it is not designed to chase moving objects for long periods. Future missions might include telescopes or spacecraft specifically built to track and follow fast interstellar visitors. Some concepts involve launching probes on short notice, using advanced propulsion to intercept objects shortly after discovery. While these ideas are challenging, the success of Webb's observations makes them feel more achievable. As time passed, the comet grew fainter. The jets weakened as it moved away from the sun. The coma slowly shrank. Eventually, 3I/ATLAS became too dim for most telescopes to observe, but by then, the important work had already been done. The data had been collected, the images had been stored. The real journey was now happening in laboratories and offices, where scientists continued to analyze and interpret what they had seen. Some researchers focused on comparing 3I/ATLAS to comets from our own solar system. They looked for similarities and differences, hoping to identify patterns. Others focused on modeling its internal structure. Some examined how radiation from space may have altered its surface over time. Each approach added another piece to the puzzle. One particularly interesting question was whether interstellar comets like 3I/ATLAS could have delivered material to young planetary systems in the past. If such objects pass through systems regularly, they might deposit organic compounds on forming planets. Over billions of years, this exchange of material could influence chemical evolution on a galactic scale. While this idea remains speculative, observations like these provide the data needed to explore it seriously. The story of 3I/ATLAS also highlighted the importance of patience in science. Discoveries are rarely instant. The images captured by Webb were only the beginning. Understanding them requires time, careful thought, and sometimes disagreement. Scientists must test multiple explanations, challenge assumptions, and revise conclusions. This slow process is what turns images into knowledge. There was also humility in the response. Despite advanced technology, scientists knew there were limits. Some details about the comet's interior would remain unknown. Some chemical signatures were faint or ambiguous. But even incomplete information was valuable. It pushed the boundaries of what could be known and encouraged the development of better tools. As Webb continues to operate, it will undoubtedly observe many more distant objects. But 3I/ATLAS will always stand out as one of the first interstellar visitors studied with such precision. It arrived at a time when humanity finally had the technology to truly look closely. Earlier generations could only imagine such encounters. Now, they are becoming real. In the quiet darkness of space, 3I/ATLAS continues its journey. It will never return. It will pass other stars, drift through clouds of gas, and remain frozen once more. It carries with it a record of its encounter with our sun, just as it carried the memory of its birthplace when it arrived. In that way, it connects distant parts of the galaxy through motion and time. For humanity, the encounter leaves behind knowledge and inspiration. It reminds us that we are not isolated. Our solar system is open to the galaxy. Material from distant stars can reach us, and with the right tools, we can learn from it. The James Webb Space Telescope did more than capture images. It opened a window to another world's history. As future generations look back on this moment, they may see it as a turning point, a moment when interstellar objects shifted from rare curiosities to valuable scientific messengers, a moment when the universe felt a little smaller, and our understanding grew a little larger. And somewhere beyond the reach of any telescope, 3I/ATLAS moves on, silent once again, leaving behind the light it reflected, the heat it released, and the questions it inspired.